Welcome back everyone. In this lecture we will continue with the definition of groups. Okay, in the last lecture we saw that if we take one Rubik's cube and then look at all possible moves that we can perform on the Rubik's cube, okay, that said with some identification. Okay, so that said we can actually define some binary operation, and we saw that that binary operation actually satisfies some properties. Okay, for example, closure property, existence of identity, associativity, and existence of inverse, all those properties were satisfied. So, that is what we saw. So, in this lecture we will continue to look at other practical examples and then try to formalize the definition of groups. So, let us look at this ice crystal flake. Okay. So, you can see that it possesses lots of symmetries. Okay. So, what we want to do, we want to actually look at all possible moves that we can perform on this ice crystal flake, and then those moves that actually still preserves this symmetry of this ice flake. So, what I mean by that, so that moves that we are performing, that actually leaves the shape of this ice crystal as it is. So, it does not actually change. So, basically it leaves this ice crystal flake invariant. Okay. So, what are all the possible moves that we can perform on this ice crystal flake? Let us see. So, one possible move, for example, what we can do, we can actually rotate 60° in the anti-clockwise direction and still get the same shape of the ice crystal flake. So, that is not difficult to see. So, similar to that, what we can do, we can also rotate clockwise 60°. Again we will be actually getting same shape of the ice flake. So, the shape does not change. For example, if you rotate 180°, sorry 120°, then again you can see that so it does not matter whether you do it clockwise or anti-clockwise, again the shape does not change. But here there is one more interesting symmetry. For example, I can take a line that passes through like this. Okay. So, here. So, now if I actually reflect with respect to this line, again the shape of this ice crystal flake actually does not change. So, I will leave it to you to think about, because it is an easy exercise. So, if you perform actually all possible moves, okay, if you just think about what are all the possible moves that we can perform on the ice flake that preserves the shape of the ice crystal flake, then you can see that. So, these 12 possibilities are there. Okay. So, the very first one, rotating 0°, that means doing nothing. So, similar move that we saw even in the Rubik's cube. Okay. And then you can rotate 60°, you can rotate 180°, and then you can rotate 180°, and then you can also reverse those process, okay, 120° and then minus 60°. So, note that rotating clockwise 180° and then anti-clockwise 180°, they result the same move. So, that is why we actually identify them. So, now like I said, so we can also reflect with respect to some lines. So, these are all the possible reflections that you can actually see. So, totally you have these 12 possible moves that leaves this ice crystal flake invariant. So, that means these are all the possible symmetries that we can get. But here what we are ultimately interested in, we are interested in a group that is actually acting on this thing. But the thing is, here I am just talking about how to rotate, how to reflect and so on. So, then what is the group? Okay. So, indeed mathematically speaking, here I am talking about the group action. Okay. So, here how the group, there is a group behind this picture. So, it is actually, if you know what is dihedral group, it is a dihedral group D6, okay, which has order 12. So, that group is actually acting on this ice crystal that we actually shown before. So, what is the group and what is the action? So, those are two things that we need to understand. Okay. So, just to explain this analogy, okay. So, before actually getting into the group definition, that is the abstraction. So, let us understand what is the abstraction means. Okay. So, if we understand this mathematical formulation, okay, then we will be able to understand what is the group behind this picture. Okay. So, let us consider one particular example. Okay. So, let us take the natural number 4. So, what comes to our mind? Okay. Are we thinking of 4 as 4 objects always? So, for example, if you are in actually in the primary school, okay, let us assume you are in first standard or second standard. So, second standard kid understands 4 as having 4 objects in hand. Okay. That is the first thing comes to the kid mind, okay, when you tell what is 4. But we are more matured. So, we actually our mathematical understanding is much more than second standard kid. So, that means what? So, we do not really think about 4 objects. Whenever we say 4, we always mean the natural number 4. So, that means mostly we remember 4 as a natural number satisfying some properties like 4 plus 3 is 7 and 4 plus 2 is 6 and so on. Okay. So, this is the abstraction that we are talking about. So, for example, if we go back to our picture that we had. So, this 60-degree rotation. Okay. So, when I talk about this 60-degree rotation, so this is that particular move that I am actually performing it on this ice flake. Okay. So, that means, so what I should consider as group element, whether should I consider as this 60-degree rotation or the 60-degree rotation that I am performing on this ice flake. So, that is the question that we are actually interested in. So, if you think about it, so what is the abstraction here? The abstraction here is this 60-degree rotation, it is nothing to do with this particular ice flake. For example, you can take any 2D object, you will be able to actually perform this 60-degree rotation. Okay, there is no issue. So, only thing is needed, you need to have a fixed point. For example, the middle point in this picture. So, you are rotating with respect to this point, that is all matters. Okay. This is that center point. So, this center point you take and then you rotate 60-degree clockwise or anti-clockwise. Okay. So, given any 2D object, you can actually, if you fix a point and you will be able to rotate. So, this is the abstraction that we should start appreciating. So, when we say anti-clockwise 60-degree rotation that we performed on ice crystal flake. So, is this anti-clockwise 60-degree rotation all about only that particular ice crystal flake? So, as I explained, the answer is no. So, we can perform this anti-clockwise 60-degree rotation on any 2D object. Okay. So, that means, so all matters is, okay, instead of looking at these ice flakes. So, what we actually consider, we consider all the possible moves that we are performing on these ice flakes. Okay. So, on the ice crystal. So, what we can do, we can start labeling them. Okay. You start giving them some names. Okay. And then you try to see. So, as we did it in the Rubik's cube, instead of studying one particular move, all we do is we take all possible moves, we study them at once. Okay. So, as I said before, that is all about group theory. So, here also what we do, instead of studying one particular move that preserves this ice crystal shape, we take all possible moves that actually preserves ice crystal shape. So, then it is not that hard to see, it will also satisfy the properties that we had for that set of moves that we performed on Rubik's cube. For example, closure property, associativity, existence of identity and the inverse. For example, identity will be that move that we do nothing. So, that is that rotating 0 degree. Okay. For example, if you perform a move that is actually, let us say, anti-clockwise 60 degree, then the inverse will be clockwise 60 degree. Similarly, for this the inverse will be clockwise 120 degree. So, for these reflections you can see that the same reflection will be the inverse. So, it is not hard to actually list down all the inverses for each element, and closure is also somewhat easier to actually think about. So, once you understand this abstraction that we are talking about only the possible moves that actually leaves this ice crystal flake invariant. So, then you take you take two moves, call it M1, M2, you first apply M2 and then apply M1. So, then you can see that M2 leaves it invariant and M1 leaves it invariant. So, you consecutively if you apply, then again that also will leave that invariant. So, that M1, M2 is also will be again a move that leaves this ice crystal flake invariant. Okay. So, but what is the most difficult part here? Actually convincing you yourself that these are all the only possible moves that we can perform on this particular ice crystal flake. Okay. So, we will come to this later when I introduce what is called dihedral group. Okay. So, sometime it is denoted by dn, but the order of the group is twice n. So, that is why I prefer to denote it by D2n, but anyway it will be very clear what we mean by the dihedral group, what is that n stands for. Okay. So, then it will be very clear why I want to call it D2n instead of dn. But anyway, so when we introduce this dihedral group, so we will actually explain everything that why we get exactly all these possible moves, and at least one part is clear, these moves leaves this particular ice crystal flake invariant, that is easy to see. And then for example, you take it as exercise, try to do possible composition of moves, okay, applying first move and then second move, and then see whether you are going to get anything new. You may actually, so what I am claiming that you will not get anything new. For example, if you apply this anti-clockwise 60 degree rotation and then if you apply this reflection, so you will be getting a move that will be one of these things. So, I will leave it to you to think about it, what it will be. Okay. So, that way at least one thing that you will be able to verify for time being. So, you take all these 12 possible moves that we are performing on this ice crystal flake shape. Okay. So, that is here. So, what I want you to verify, for example, the closure property. If you take any two of these, you compose them. Okay. That means you apply, for example, what is M1 composed M2, you apply M2 first and then M1 later, then you are getting a new move. So, that new move, what I am saying, it will be one of these 12 only, you do not get anything new. Okay. And already I pointed out inverse will be what? Okay. Associativity, so once you understand this as maps, okay, satisfying some properties, then associative will be somewhat trivial. Okay. We will do that later when I introduce dihedral groups. Okay. So, we will also study properties of dihedral group in that lectures. Okay. So, now I believe all of you must have got some idea about where the groups are coming from. So, like I said, so groups do not arise alone, they always arise with action. Okay. Groups without action does not make any sense, at least for me. Okay. For example, here we talked about this dihedral group D6. Okay. It is naturally acting on this particular ice crystal flake, but it is one example where it is acting. You can actually change the shape of this also. For example, you can talk about 6 gone. Okay. So, if you take 6 gone, then D6 will act on that 6 gone. So, that is something we will be seeing. Okay. So, there will be more objects on which given one group can act, but we need to understand abstractly what is that one group, okay, that group definition. So, that is where we are converging. So, from the examples that we have seen so far, so one is the set of all moves on Rubik's cube that we can perform, and here again set of all moves that we can perform on this ice crystal flake. So, that suggests that, so all we do is you can start with a non-empty set and then you define what is called binary operation on that. So, that means given two elements from that set, you want to uniquely associate another element from that set, okay, and that association must be unique. Okay. So, that means, so we can, so most of the things that we actually talk inside mathematics or define in mathematics, that can be defined using what is called sets and functions. So, we have to use the language of sets and function to define anything. So, if we use the language of sets and functions, so then what we have a set which is non-empty set and a binary operation which is a function from G cross G to G. That means, given two elements, you can call it order tuple AB, then you are associating one element with that AB. So, the order matters a lot, because when I say I actually take element that is associated with given two elements AB, let us say the order is given to be tuple A comma B. So, the corresponding element I take it to be AB. Okay. It is just a notation. So, like we did it for the moves. Na? So, when we talked about the moves that we performed on the Rubik's cube, I said when you take M1, M2, so that means you apply M1 first and then apply M2. But it is not hard to see applying M1 first and M2 first does not amount to be same as applying M2 first and then M1 first. Okay. So, in the language of group, it is called commutativity. So, not all groups are commutative. So, let me start writing a bit. Okay. So, here we are ready to actually define a group. So, we need a set. So, that is the first thing. You start with the non-empty set, and given two elements, we need another element that is uniquely associated with group G. So, that means you have a operation, okay, binary operation from G cross G to G. So, that is just a function. So, most of the time this function will be denoted by just dot, okay, because the operation is just one operation. It is custom to just write it as either star or dot or without anything. Okay. So, let us use the customary notation, that is star. So, given AB, so I am going to associate some element inside G. So, because we do not know what is that element, we just denote it by A star B, that is all. So, recall, if we take the set of all moves, that we can perform on a Rubik's cube. Okay. So, that set you can take it to be G. Okay, let me call it GC, because that C is the Rubik's cube. So, then what we did, given M1, M2 from this G of C. Of course, so there is this identification modulo the identification that we just write it as, yeah. So, move with some identification. So, given M1 M2, what we did, we said what is M1 star M2, which we denoted by M1 M2. What we said, so first we apply M1 and then we apply M2. Okay. But it is not that hard to see. So, first applying M1 and then applying M2 is not same as first applying M2 and then applying M1. So, you can easily find some moves M1 M2. So, for which M1 M2 is not same as M2 M1. Okay, that I will leave it as exercise. You just find those two moves on the Rubik's cube. So, now, so that means the order in which I associate this element, that matters a lot. So, that is why I take this order tuple A comma B and then send it to A star B. Okay. In general, A star B is not same as B star A. So, what are all the things that actually this G and star satisfies? Okay. So, the closure property is encoded here, star being a function. So, given A comma B, you have this A star B, which is an element of capital G. So, that means already it is closed under this binary operation. So, the second condition, which is indeed the first condition, is the associativity. So, what is the associativity? So, if I start with 3 elements A, B, C inside G, then there are 2 ways to perform this A star, B star, C. Okay, that is what we saw in even for the Rubik's cube. Okay. So, first we can do A star B and then take star with C. Okay. But what is associativity says, this is same as you first take B star C and then take A star B star C. So, these two things are true for any ABC. So, the second condition is actually the existence of identity. So, what it says, so there exists an element E in G. So, it is customary to actually denote this identity as E. So, later we will prove that. So, this existence of identity already implies that the identity is actually unique. So, there exists identity E in G such that when you perform A star E and then E star A, then that should be A for all A in G. So, that means this identity does nothing when you compose with A, and there is this existence of inverse. So, what it does? So, there exists given A in G, there exists B in G such that A star B is same as B star A, which is same as identity. So, it is like the reverse move, okay, that we actually had in the Rubik's cube. Okay. So, that is something. So, abstractly speaking, it is just a non-empty set with the binary operation. So, given 2 elements, you should be able to associate another element in the G in a unique way, and it satisfies the following property: associativity, existence of identity and existence of inverse. If G star satisfies these properties 1, 2, 3, okay, so that is called group. G star satisfying 1, 2, 3 is called a group. Okay. So, that is what group means. So, we saw two examples so far. Okay. All possible moves that we can perform on the Rubik's cube with respect to the composition of moves form a group, and all possible moves or all the possible symmetries that are there on the ice crystal flag that we saw. So, that also form a group. So, these examples again can be generalized. Okay. So, there are various symmetries actually that we can actually talk about. Okay. So, we can change the shape. For example, we can take triangle and then we can talk about all possible symmetries of this. Okay. So, even before triangle, what we can do, we can actually start with a line segment. Okay. You just take a line segment. So, line segment, let us say inside your R2, or you can also talk about symmetries of these letters. So, this is something you must have seen. Okay. So, what are all the symmetries are possible for given alphabets. But anyway, so we will make all these things very precise. Okay. And then we will see more and more examples coming from number theory, geometry as well as combinatorics. Okay. So, we are running out of time now. So, I will stop here. So, we will continue with some more examples of groups coming from number theory in the next class. Thank you.